In the previous video, we looked at a couple of examples, and some of them had absolute maximums and minimums, and some of them didn't, right? So the natural question to ask is, well, do we have any kind of, result that tells us when we're going to have an absolute max and min and when we're not necessarily going to have an absolute max or min? And so, yes, we do. It is called the extreme value theorem. Now, I'm not going to prove this theorem for you. It's a little bit extensive, involved. If you take an advanced calculus course or introductory analysis course, you'll see the proof there. But it makes some intuitive sense. So we're just going to talk about it. So what we need two things. We need our function to be continuous, and we need our domain to be a closed interval. Because remember, we talked about the absolute max and the min being dependent on the domain. So if we have those two hypotheses going on, a continuous function on a closed interval, then we can say for sure there is an absolute maximum attained and there is an absolute minimum attained, right? So the important things are, so your hypotheses are for this result, f is continuous and your interval is closed. And it makes sense because the fact that the interval is closed means that you have closed circles at the endpoints, right? So, and the fact that f is continuous, it means you don't have any jumps. So you can imagine pictures like some things that we saw, right? Where here, the maximum happens at the top here, the minimum then happens there, or maybe both the maximum and the minimum happen in the middle of the interval, right? That might happen. But what you can't have, because f is continuous, is like you can't have a hole there. That wouldn't work, right? Then it would be discontinuous. Or what would happen if, let me get rid of that and put it back. What would happen if, let's say, you had an open interval, right? So let's say I had open circles here. Well, it kind of looks like that would be the minimum and that would be the maximum. But remember what we said, it actually has to attain that value. Here, you're never going to get down to that value, and you're never going to get up to this value because it is an open circle there. Of course, the limit is there, but the actual value, it has no value. F of B has no value. F of A has no value. So it doesn't attain the value because it's not there. It's an open circle. So I have basically a couple of quick examples just to sort of help you see like where this can go wrong, to give you an idea of why we have these two hypotheses for the intermediate value theorem. And of course, like drawing these things with decimals, it takes a minute. So this is just the function 1 over x plus 5. And I'm looking at here the open interval from -5 to 5, right? I'm taking an open interval. And this function is perfectly continuous on that open interval, but the interval is open. So even though the function is continuous on the interval, it's going off to infinity at the left endpoint, right? So I'm never going to have a maximum value because it'll always go off towards infinity. And at the bottom, if this was closed, then I could say that, yes, I have a minimum of 1/10 at the right endpoint. But because it's not closed, I never reach the 1/10. So I can't say that 1/10 is the minimum. So this is a function, because it's on an open interval, fails to have both a maximum and a minimum, right? So there's no absolute max and there's no absolute min because I took this open interval, even though this function is continuous. Now, if I took a closed interval, I would no longer have a continuous function because this function wouldn't be defined at -5. So it would fail for the other reason, right? Here's one where my functions are kind of nice in the sense of they're not going off to infinity, but it's a discontinuous function. So you see what happened. It basically, this function is, again, I'm taking now the closed interval from -5 to 5. So I'm thinking about the opposite situation where you have a closed interval, but you have a discontinuous function. I could also have used something like whatever, 1 over x or something, and given it a value. It doesn't matter. You can do all kinds of different things. But I do want my function to be defined for the entire domain, right? So if I did use something like 1 over x, I would have to put a dot in there. But in any case, I decided to just use these lines. So this is line y equals x, but there at x equals 3, we jump down to this one, which is, of course, y equals x minus 4. And there's an open circle here, closed circle there. Why? Because now there's no maximum, right? Because the maximum would be 3, but we never get to 3. So it doesn't have a maximum. Whereas what does have a minimum, the minimum would be here. That's the absolute minimum is -5. So just because a function fails on not having a maximum doesn't necessarily mean it doesn't have a minimum. You have all different things, right? So that's just some idea about the extreme value theorem. Now, what's the importance of the extreme value theorem? You will see in a minute, in the next video or two. The importance of the extreme value theorem is that if you have the situation where f is continuous and the interval is closed, then you know that you do have to have an absolute min and an absolute max, and then we can solve for them.